Hey, welcome to our flipped lesson on graphing logarithms. So we spent some time graphing exponents, and we found that the Birath technique always works, where we look for the new origin and we find where that new origin is, and then we strip our function down to its bare parent function, its bare essence. No adding, subtracting, multiplying, or dividing, just the basic function. And then we make a table of those movements from the origin. But today I want to look at graphing logarithms. And if you recall, we know that logarithms are exponents. So how do we graph logarithms? Well, first of all, let's start out graphing an exponential function, just to get it back into our head, how we do this. We'll graph f of x equals 2 to the x. So notice there's no shifting, there's no adding or subtracting. So my origin will be the origin, 0, 0. And so I'll strip this down and make a table of those movements. Well, this is already stripped down. I'm not multiplying or dividing it by anything, so we can make a table of those movements. So my starting lineup of -2, -1, 0, 1, and 2 is here. Spoiler alert, I thought we might add a couple points beyond that, so I put in -3 and 3. So we put these points into this function for x. When we put in -3, 2 to the -3rd is 1/8. 2 to the -2nd. Remember that negative exponent flips. 1/4. We get a half. 2 to the 0 always stumps kids. Don't get fooled. It's 1. 2 to the 1st. 2 to the 2nd. 2 cubed. And then I could go ahead and I can graph these movements from the new origin. Now, the new origin is still the original origin, nothing shifted. So go over -3 up 1/8. Oh, -2 up 1/4. -1 up 1/2. You'll notice it's not that impressive. Go over 0 up 1. Go over 1 up 2. Go over 2 up 4. Go over 3 up 8. Over 3 up 8. We're there. And then if we draw this with a nice smooth curve, I'll try it. I'm not that good with the mouse, but oh, Mr. Birath, look at that fabulous curve. And then you have to think about this. Is this graph ever going to touch the x-axis? Will the y value ever actually become 0? And the answer is no. It won't. There's no power, real number power, that you could raise the number 2 to in order to make it become 0 or even become negative. So we always want to remember that there's an asymptote here. I just have to find where I put it. There's an asymptote. There it is. Yeah. So that's y equals 2 to the x. But what I want to do today is I want to graph logarithms. So let's graph this. Okay. F of x equals log base 2 to the x. Now, we look at that and I think, oh my gosh. And one of the things I've told you over and over and over again in this unit is I am not very good at logarithms. But what I am really good at is exponents. So maybe what I do, if I'm not really good at logarithms, is I'll call f of x, y, and I'll rewrite this logarithm as an exponent. And if I rewrite it as an exponent, well, I'm awesome at graphing exponents. So let's switch from logarithmic form to exponential form. Now we've had several lessons on this. Remember, let's see, the base is 2. So 2 raised to this number, y. Remember, logarithms are exponents. 2 to the y equals x. So this is what I want to graph. 2 to the y equals x. So I'm going to set up an xy chart. And let's think about this for a minute. What numbers do I want to put in here? You know, looking at this equation right here, it seems to me that x's and y's are kind of switched from how I'm used to having them. Normally, x is the independent variable and y is the dependent variable. Y usually depends on x, but in this case, it's switched. So I think what I'm going to do for the first time ever is put my starting lineup in for the y's. Because y is the independent variable and whatever y is generates our x. So if I do that, switch the x and the y's, I'll put that starting line up in here for the y's, and when I put -3 into this function for y, I get 1/8. And then -2 gives me a fourth, and -1 and 0 and 1 and 2 and 3. And so I can graph this logarithm by plotting these movements from my origin. So from my origin, I'm going to go right 1/8 and then down 3. Oops. All right, you shouldn't have seen that. I'm going to go right a fourth and down 2. Oh, there it is again. Don't look at that. I'm going to go right a half and down 1. Again, I'm just plotting these x, y movements. Right 1 up 0, right 2 up 1, right 4 up 2, right 8 up 3. And then I can draw this nice smooth line right here. And, oh, okay, let's pretend that didn't waver off. Again, I'm trying to draw this with the mouse. And you know, we would have that question of, will this line ever cross the y-axis? Will there ever be any value for y that would make the x 0 or make the x negative? And the answer is no. So we see we have this vertical asymptote. You see, when I look at these two graphs, this blue graph and this red graph, I see they're related to each other. It's almost like that they've been reflected right across this line, this green line, y equals x. And if you remember from our lesson a few weeks ago, that's the whole idea of an inverse. An inverse graphically of one function is where you flip it across this line y equals x. Algebraically, what an inverse is where you switch your x and your y values. Notice if I switch these two, I get the logarithm. And remember, algebraically, the way we found inverses is we physically switched the x with the y. So logarithmic functions are just inverses of each other. They're where you switch the x and the y value. So very interesting. And that takes me to this big point that I would like to make, and that's that I never graph logarithms. I only graph exponential functions. So let's take a look at how we would do this ourselves with a different base. This time f of x equals 3 to the x. So I have my normal starting lineup. My y's have changed because my base has changed. This time, instead of taking powers of 2, I'm taking powers of 3. If I go to graph the inverse of this function, which is a logarithm, then what I do is I say, well, let's rewrite this logarithm in exponential form. Instead of y equals log base 3 of x, I rewrite it so it's 3 to the y equals x. And once I rewrite that in exponential form, I realize that I want my starting lineup right here for the y's. I put those y values into this equation and it generates these x's. And then once I have that table of movements, I just plot those movements. From my origin, I go right 1/27th, bloop, barely perceptible, and down 3. I go right 1/9, again, it's barely any movement off the origin, and down 2. I go right 1/3, down 1. I go right 0, up 1. I'm going to go right 3, up 1. 1, 2, 3. I'm going to go right 9, up 2. And then my next upward movement, I'd have to go right 27. Holy smokes, that's off the page. So then I just draw this nice smooth curve. Quit laughing. I'm drawing with a mouse. It's very challenging. I hear some of you laughing at me. And oh my goodness, look. Okay, that was terrible. It shouldn't dip down, but it's slow. And this is a really good time to point out that if exponential growth is explosive growth, once it takes off, man, it really takes off. Logarithmic growth is very slow growth. Look at once we cross that that 0.10. Look how slow the growth is. The next time I go up a block, I have to go 27 units out. Such slow growth. That's logarithmic growth. Well, let's get and do one more example. Let's take a look at what happens if we've got some changes. So here is our third example in your notes. What if I've got some things going on in this logarithm, some adding or subtracting? Well, we're going to approach this the same way we approach any graph. The first thing we do in the Birath technique is we find the new origin. Now remember, the process for doing that is we set whatever's inside the function, x minus 3 in this case, we set that equal to 0 and we solve for x. So I'll bet you've already solved this. I'm painstakingly writing this with the mouse. And we get x equals 3. So my new origin, the x value is going to be 3, and the y value is going to be right there. It's going to be 2. So very lightly, I'm going to use this yellow ink because you can barely see it. At the point 1, 2, 3, 1, 2, that point right there is my new origin. I don't want to mark it with my regular pen because the graph isn't necessarily going to go through that, but that's going to be my new starting point. Then I take the basic function. This basic function is y equals log base 2 of x, and that's what I'm going to focus on for making my table of movements. Now, I'm not really good at logarithms. As a matter of fact, I think I just told you I never graph a logarithm. So what I do is I use my powers of converting logarithms to exponents. The base is 2, the exponent would be y, and that's equal to x. And that is how I'm going to generate this table. I'm going to move this right here, and I'm going to generate all these x values based on these starting y values. So I'm going to put those in, doing my math, and then from the new origin, I'm going to plot those movements. From the new origin, first I move right 1/8 and down 3. Holy smokes, barely off that value, down 3 there. Right 1/4, down 2. Right 1/4, down 1, 2. Right there. Right 1/2, down 1. Oh, there it is. Right 1, up 0. Boom. Right 2, up 1. 1, 2, up 1, boom. Right 4, up 2. From the new origin. 1, 2, 3, 4, up 2. Right 8, up 3. 1, 2, 3, 4, 5, 6, 7, 8 would be about here, up 1, 2, 3, and then I draw this nice smooth curve. Oh, that's not bad. That's not bad. That's pretty good there. That nice smooth curve right there, and there's my graph. Is that my graph? No, it's not. Remember, it's asymptotic. So I'm going to go ahead. I'm going to go ahead and put an asymptote right through my new origin. Boom. It's in green, so it really sticks out. That's my graph. Well, based on today's lesson, I have a couple more graphs I want you to fill out in your notes. And then when you're done with that, there's some homework to work on. So good luck. And remember, I never graph logarithms. I graph exponents. Good luck.